So what we would do is we would have a megawatt of our energy going through. If we were to feed that to a unit under test, maybe a UPS, or it could be a AC to DC converter, or a solid state transformer, or a transformer. Ideally, that energy would go through that device, and it could go through another regenerative product that could either be DC to AC or AC to AC, feeding that back into the utility. You're just looking at the losses of the two energy devices that we have and a unit under test.
Hi, I'm Mark Rogers with the Data Center Engineer, and today we'll be discussing AI server power testing from infrastructure to data center to rack. I'm joined today by Mike Nolan of PPST Solutions. Thank you for joining us today, Mike.
Glad to be here, Mark. Thank you.
For those that aren't familiar, can you quickly tell us a bit about PPST?
Sure. PPST is a leader in power supply testing and power, AC sources, DC sources, DC electronic loads, AC electronic loads, bidirectional. We also perform system level solutions that are for EMC, harmonic and flicker, and also some fast acting switches.
So the first question I'd like to get into is around AI power testing and what it actually looks like. When we talk about AI server testing, we're not just testing one power supply, we're looking at the whole system. Can you walk us through what a typical data center power setup looks like?
Absolutely. When you were to look a few years ago from a traditional data center, you ideally had AC input coming into the facility. They're fed primarily to transformers that step down that voltage. You had UPSs that were very large, megawatts, and again, battery backup, feeding that for the ability to have backup. You had diesel generators. You had a host of other backup equipment, automatic transfer switches, power distribution units that fed that AC, again, to the server rack. And from there, you step down and had the ability from an AC to a 48 volt that fed to the individual rack servers. In today's market, you have that traditionally also being served in that manner, but you have things now coming in through the AC, which is now what they call SST transformers. And so they're taking AC, transferring to DC, ideally having DC backup to that also, or it could be straight AC, but now feeding an 800 volt DC bus and stepping that 800 volts down to ideally a sub 5 volt level, and thereby bypassing a 48 volt step down that typically took place in the server rack. So power itself has evolved, different approaches, and within that, there's a host of components. And what I mean by components, it's AC to DC, DC to DC, circuit breakers, ATS switches, transformers, and DC to DC converters that have to be tested to ensure reliability and safety.
When engineers are testing power systems for servers, what are they really trying to prove? Is it mostly about efficiency, reliability under heavy load, handling power swings, meeting compliance standards, or is it all of the above?
Yeah, Mark, it's all of the above. And when you look at from the early stage during R&D, where design work is being done, you definitely are testing at a performance. As you get further into that engineering design process and even an evaluation, you're ideally testing your specs and your safety to ensure that you're capable of meeting, producing a product that would fit into the market space and be very usable. Reliability is key. So again, your evaluation team would definitely spend the time to ensure that from a longevity point of view, these products are going to be capable of being put into the AI facility and operating for many, many, many years.
Why not just use utility power? a lot of people might assume you can just plug into the grid and test. Why do data center designers use programmable AC and DC power systems instead of relying on normal utility power during validation?
Great question. In test, it's key to test ideally your four corners, as they call it, meaning high voltage, high current, low voltage, low current, and ensure that your product is going to perform correctly. How that changes and the rate that it changes, ideally, is something that is an anomaly that takes place in the with the utility company. And so to have repeatability in tests to ensure you understand where your product and how your product performs under those conditions needs to be done in a very precise and accurate manner. By using programmable test instrumentation, you're able to set those conditions very accurately before the repeatability wise will ensure that you're able to test and create fault conditions and ensure that when the fault conditions do occur, what occurs, what happens, and be able to ideally ensure that your products can handle those fault conditions without having a catastrophe or a failure that's irrecoverable. You want to ensure that you can test things that are able to survive. Ideally, someone runs a car into a telephone pole, and a telephone pole sends a surge. The ability for your input, the utility company, to their AC facility power of your AI center doesn't have a voltage so high that it shorts out your input. So having fault clearing devices on there is very important to ensure the reliability and longevity of running your AI center for a long time.
Speaking of servers, especially GPU clusters, we know that they can ramp power up and down very quickly. So, how do you simulate those fast changing loads in the lab environment? And what kind of DC load capabilities are needed to realistically test that behavior?
Great question. And again, having been in the DC load market for over 25 years, I'm seeing
Right.
definitely over the years that definitely the speed of all of the chipsets and the power and the peak demand, this current has gone up and up and up. When you traditionally look at from a loading perspective, again, low voltage, high current on that side of the GPU. Again, that is coming and feeding also to the DC to DC converters that ideally have to respond to that. So you need an electronic load. There are switchers, which means a power load that could switch the energy. Ideally, those are working in maybe a millisecond or ideally a little less. But to truly meet the requirement, linear loads are required, meaning that the instantaneous current demand for a lot of these linear loads are in the 20 or 30 microseconds or faster. There are some loads requirements that are in the nanoseconds, and those are kind of unique in aspect. And there are some unique capabilities that people have to be able to meet that requirement. But traditionally, linear loads are being used for testing, and again, challenging the control loop of those DC converters that are feeding those GPUs and ensuring that they're capable of meeting that power demand.
I wanted to ask about large scale burn in testing. We know at the megawatt level, running long burn in tests must consume a huge amount of energy. How are companies managing that today? And where do regenerative test systems really make a difference?
This is something from a power point of view that I would say has been only in the last 10 years that's really been addressed in the marketplace. As an example, PPST solutions, we have to also burn in our own equipment, as you can imagine. So if we have a 1 megawatt solution that we're building out, ideally we're drawing 1 megawatt of energy plus from the utility. That's a lot of power to draw, and the cost can be very significant over time because, again, we're running for maybe 24 hours. There are some people looking to do a burn-in to ensure reliability and that infant mortality rate, meaning that 90% of failures occur within 12 hours of operation, to ensure you cover those bases and you don't send out equipment that the customer receives. And again, this is for all typically power products that have a burn-in for a long time, meaning over an hour. So what we would do is we would have a megawatt of our energy going through. If we were to feed that to a unit under test, maybe a UPS, or it could be a AC to DC converter, or a solid state transformer, or a transformer. Ideally, that energy would go through that device, and it could go through another regenerative product that could either be DC to AC or AC to AC, feeding that back into the utility. So the picture that we're drawing here is when you look at from an energy loss, you're just looking at the losses of the two energy devices that we have and the unit under test. And when you do that, all thing you're paying for from utility is the energy losses, and all those sum together. So ideally, in our case, we're going back to back. So that's typically less than 10% of losses of energy that we're having. So we're burning 1 megawatt, out of 1 megawatt, we're only utilizing 100 kilowatts of energy. The rest of the energy is just circulating. What that means is we're not drawing 1 megawatt from the utility company anymore. We're just drawing 100 kilowatts. And so our energy consumption drops down by 90%. And if you're looking at a 24-hour burn-in, especially in California, as you can imagine, those rates can be very high. And the other thing that you have dilemmas with is that in today's environment that we live in, a lot of data centers, or if you look at testing of these components, high power, the companies may be in an area whereas during peak energy times, the utility companies require them to reduce their energy consumption. By using this approach of having your ability of testing and regenerative your energy as you're testing, you're actually consuming less from a utility company and you're reducing your cost. So any product that is now taking energy in or out, by doing that in a bidirectional mean, connecting to the facility, you're consuming less energy, you're saving space, because again, you're not requiring to remove the heat in the facility. So there's also heating costs that you're reducing. And when we look at also from a human factor, if you were just burning 1 megawatt of heat in a facility, it would get pretty hot very quickly.
Right.
And so it would be very uncomfortable. So from a human factor, this also addresses that to make it more compliant with state and local regulations for environments that people have to work in.
If a company starts, for instance, by testing a single rack, how do they scale that to validating an entire data center's power infrastructure?
Yeah, that's a great question, because there's not one size that fits all. Some data centers are based upon older 10 kilowatt server racks. Some could be based upon 100 kilowatts. You're going to have a combination of all the above. The future is coming, which is a 1 megawatt server rack. So as we look at that and we understand that there's not one solution that catches all. In our case, on Pacific Power Source, what we do is we focus on modularity. And so that gives us the flexibility, whether that's in parallel or seriesing our modules that's on the AC side or the DC side. It enables us to grow from a maybe 5 kilowatt all the way up to megawatt-plus on the AC grid side. Mm-hmm. And on the DC side, it enables us to go from a 5 kilowatt well over 3 megawatts of DC, whether that's sinking or sourcing, meaning taking the energy or providing it. and all those products can be regenerative to get that cost savings from uh, exorbitant energy, feeding it back to the utility if required.
As the data centers move toward higher voltage DC distribution, and also on-site energy storage, and even microgrid integration, how is power testing evolving at the facility level, not just at the rack level?
Right. That's a very interesting question, because when you look at the market space that's out there, we all understand that from a utility point of view, we realize that all of us at home want to maintain our homes with air conditioning and have electricity available.
Right.
It's been well established that the utility grid is not capable of allowing these gigawatt, I should say, facilities to be built and put into the areas that now are going to take city type power away. So what is interestingly happened is you have other topologies being added into the mix. So it's no longer just a utility facility input power. We have now things like fuel cell. So now the ability to have gas or hydrogen feeding a fuel cell that's going to be able to support the actual power requirements at a very large megawatt. We have smaller nuclear power plants that are in play. So
Yes.
companies coming out with that approach. With all of these and above, we also have the need for reliability of energy. The cheapest and probably the most effective way of having that is through batteries. And so energy storage also falls in play. The change with the 800 volts on the DC side really adds a dynamic. Whereas traditionally you had an AC coming in and feeding to a UPS or through a transformer to a UPS for the large power, and that UPS, which is an underripple power system, that's converting AC to DC and having that DC link connect to a battery bank, very large, megawatts worth, because ideally you want backup, and feeding that to a DC to AC output, and then feeding to a PDU. All that, you lose efficiency. So if you could take a stage and keep it 800 volts, let's say a solid state transformer, take the AC to DC, have it 800 volts, you now reduce that DC to AC stage in there, and that increases your efficiency. So now your efficiency increases. So now you can add your 800 volts directly to a battery bank and have that as storage. You could also take that now and feed that, because again, Ohm's law says if you increase the voltage, you decrease the current. So for the same power. So if you're performing that function, what you're doing is you're using less copper. Well, again, we can understand for a conduit running that through the miles plus of cabling that's required inside of a data center, there's energy savings on that front and cost savings up front. So what we're doing is we're improving the efficiency of the data center by raising that to an 800 volts DC, ideally eliminating the 48 volt, because again, they're stepping the AC down to 48 volts before it goes down to the GPU. Now they would take a DC converter, stepping 800 volts down to the lower voltage, which would be 2 volts or below, ideally for the GPU. And therefore, by eliminating stages, you increase your efficiency. So there's a lot of reasons why to make the changes. There's a lot of reasons to look from a reliability point of view, why relying on the utility is not the most economic sense. You need these other topologies that ideally could be backup as primary. Diesel generators, utilize a lot in the marketplace. Places like in California where air quality control, you can only have diesels on for so many hours under emergency conditions before they have to be turned off. And from a AI data center, it's not how they can make money by turning off and turning back on.
I know you touched on this at the beginning, but can you tell us a bit more about what role PPST solutions plays in the data center space?
Absolutely. PPST has been a leader in the test and measurement for over 50 years.
Right.
Primary focus has been in the AC market. We've been a leader in the avionic, again, for frequency converters, for AC sources. We've playing a major role now in the renewable energy, simply because now from an AC point of view, you not only need to load some of these data centers and UPSs and other AC products, but from a sourcing point of view, you also need to do grid sim. So the ability to meet standards 1547, 1741, perform anti-idling tests. Again, if utility power drops out, how exactly does your inverter handle that? So the ability to meet certain IEC standards and requirements are very important. We're also playing a key role in the DC sourcing and loading market, testing for bidirectional devices. And again, this covers a wide range. You know, as I always say, planes, trains, and automobiles, it's electrification. So
Right.
I don't, well, AI has a requirement for a fuse or a requirement for a transformer to be tested. There's a lot of other industries that have the same, whether that's in the Department of War or that's in the medical field or whether that's in a avionics world. Uh, Power is power, and the ability to have products that can test and challenge the limits of again, all those products are being built for the data center now for power. We have the ability for testing those. So a lot of our customers that are traditionally have been in the other market spaces are now in AI space simply because it's a natural transition. 800 volts, as an example, is a key growth area for power in the automotive. Before that, 600 volts was kind of the limit on the DC side for a lot of requirements, simply because of safety and availability of components. You couldn't get devices that were rated above 600 volts from a safety point of view, DC. Now, because automotive went 10 years ago from 400 volts and moved it to 800 volts, the availability for the data centers now to use that topology and technology to integrate is available. And again, Pacific Power Source under PPST Solutions has the ability of having products to be able to test all those products.
We're seeing that a lot with many folks who we're chatting with in terms of a lot of learnings from the past 10 years and the mobility space moving over to the data center space.
Absolutely, that's a key point, Mark. I mean, I would say it's a learning curve that it's great to see that a lot of familiar faces from the automotive electrification is now coming over to the AI powering world, and it's really fueling the growth of this um, need that needs to take place. Because again, we're not building any massive utility facilities to handle this power. So how these AI centers handle the power and what they use, it's very dynamic right now. And again, but that testing requirement in power, there's a lot of set standards and performance wise that it needs to be done that Pacific Power and again Pacific uh, we can edit this part. So just to say that,
Yeah.
so all the PPST solutions has the capability of doing unique testing, whether that's voltage, current, as voltage sources, current sources, or DC electronic loads. we have a slew of those solutions in play to help out from the sub kilowatt to megawatt.
Well, I appreciate your time today. Thank you so much for joining us and sharing your expertise with us.
I appreciate it, Mark. Thank you for your time today.